Hello, this is Doug Montgomery, and I would like to welcome you to our second Fireside Chat. I hope if you were here for the first one, I hope that you enjoyed it. Before we get started, I want to again thank some people that were very instrumental in putting our courses together. Scott Mahler, who did a lot of the work interfacing with Coursera, Tom Arcus, who did a wonderful job in recording the lectures that I did and the lectures that Carly Metcalf did on Jump. Amy Kitchens, who just did a terrific job in taking a lot of the stuff that I did and turning it into through her course design skills, turning it into something I think that was a big improvement over what I did. Justin Hampton has done a great job with the production of this, and Megan Gibson has done a really wonderful job in helping me figure out how to manage a lot of this and take care of take care of the questions during our QA. She's just been an enormous amount of help. So those are all people that I really owe a debt of gratitude to. And in particular, I want to mention Carly Metcalf, who did such a terrific job with the jump videos, and she's actually going to be here a little bit later on today as a special guest for our fireside chat. What we're going to do today is we're going to have a couple of presentations. I'm going to do one, and Carly's going to follow me with one. And then we're going to follow that with some questions that I'm going to try to answer for you. And as usual, I'll try to answer everything that comes in while we're on air. But if there are questions that we can't really get to because of time or because of the elaborate nature of the question, then I'll try to get an answer written up and back to you in some sort of really efficient way. It turns out that if you did not get to attend the first fireside chat, they are recorded and they are posted in Coursera. And this is the we're going to show you the information where they're available. I think it's coming up in a minute here. Yeah, there we go. This is the location where you can find them. They're in the resources tab for the course, and we're gonna post all of the recordings from the fireside chats there, so you can if you miss one, you can take a look at what we did during that presentation or during that program. Okay, so with that, I think we are ready to get started with the main event this morning. And I have a presentation for you that I hope you're going to enjoy. And we're going to get it up here so that you can see it in just a minute. Here we go. There's the info about the recordings. And now here is the start of the presentation. Many of you know that I have written an experimental design textbook, and the textbook is in the it's in the 10th edition, and almost all of the editions from about edition 5 onward have had grapes on the cover. And lots of people have asked me, why do you have grapes on the cover of the book? What's that all about? Well, there's a story about that, which I'm going to tell you. And here is a well-known joke in the wine business, which I hope you'll appreciate. It's how do you make a small fortune in wine? And the answer to that question is you start with a large fortune, okay? Because vineyards and wineries are black holes for quite a long time. They're money sinks. And unless you've got some significant resources to invest, it's going to be a long time before you actually see anything in the way of positive cash flow. Well, I have a long history of personal experiences with grape growing and winemaking. And part of this stems from the fact that I discovered at a very early age that I could not drink beer. Beer makes me physically ill, really, to the point where I become part of the entertainment. There's certain kinds of hard liquor I like. I like good bourbon, but one drink and I'm asleep. That's not very useful either. But I discovered that I could drink wine, and I enjoyed wine. I developed a reasonably decent palate for wine. So in mid-80s, 84, I found myself at the University of Washington, and I was doing consulting work with a company down in Oregon. And I got to be very good friends with the engineer that I worked with mostly on these projects. And he told me one day that his life's ambition was to be a winemaker. And I said, well, Harry, what's stopping that? And then that's when he told me the old joke, how do you make a small fortune in wine? And I said, well, you don't have a large fortune. Why don't you get investors together? And he said, that's what I'm working on. He had bought some vineyard property in Newberg, Oregon in 1983. And he was getting investors together so that they could start growing grapes and turning the business into a winery. And so I joined as a partner in this. Now the only problem with this was that none of us were winemakers. None of us really knew much about this. Now you can learn a lot by just reading. It turns out that the University of California, Davis has a wonderful winemaking program. There's a lot of literature, and you can learn a lot by reading. The mid-80s was an era where winemaking and wineries in Oregon were really starting to boom, in particular growing Pinot Noir. And we had a couple of winemakers as partners in our venture because they wanted to buy grapes from our vineyard. Some of the partners, though, principally Harry and myself, knew the power of designed experiments. And I remember Harry making a statement that said, winemaking is a chemical process. He said, when I took my first job as a chemical engineer, I didn't know how to make polymer either, but we figured it out, and we used designed experiments. So we decided that we would use designed experiments to develop our winemaking process. Now, there are a lot of factors that you can investigate. If you scour the literature and you talk to the French, who have been making Pinot Noir for many years. We planted Pinot Noir, by the way, because that seemed to be the popular thing to do. There was a lot of information that we could gather about what factors might be important. We had a list of probably somewhere between 18 and 20 factors that we could possibly investigate. We decided, Harry and I, that we would never have more than 8 factors in any one experiment. And by the way, only one experiment a year is feasible because you only get one crop of grapes. And so what you learn from year 1, you're going to have to apply in subsequent years. We focused on Pinot Noir because that's what we wanted to grow and what we wanted to make. And so here is one of our early experiments. This is from 1985. This is probably the first year that we actually ran a formal experiment because we bought the property in 83. 84, we cleared the stumps, we trellised, we planted. So this is 85. And if you look at this list of factors, we have 8 factors. the clone of Pinot Noir. We really didn't know which clone we should plant, so we picked two of the popular ones that had been planted in Oregon, Primard and Dansville. What kind of oak do you use to ferment the wine in? Because you use oak barrels. There's lots of places to get oak. There's American oak, there's French oak. The folklore says that you really need to use French oak, but there's lots of different kinds of French oak. And so we settled on French oak barrels from two different regions, Alias and Tronquet. Is the barrel old or is it new? Is it a used barrel? An old barrel is what we think of as neutral oak. It's not going to impart nearly as much oak flavor to the wine. Yeast, type of yeast you use, and the skin contact method that you use. You can always use native yeast, but there are other types of yeast that you can use, and here are two that seem appropriate. When you crush the berries, do you have any stems in the fruit? Well, you can leave them all in, or you can get them all out. You toast the inside of the barrel. You burn it a little bit. Do you do a light toast or a medium toast? And there's other levels of that too. Do you include whole clusters along with the fruit? This is the major stems that the fruit is attached to. And then the max fermentation temperature that you're going to allow is another factor that we could use. So we had 8 factors, and we decided on an experiment with 16 runs. Here is the actual experimental design that we used. This is a 16-run fractional factorial design. It's a 2 to the 8 minus 4. And if you're in the second course, factorials and fractional factorial designs in our MOOC, you'll learn about these designs. This is a resolution 4 design. So that means that the 8 main effects are all clear of 2-factor interactions. They are aliased with 3-factor interactions, but the 2-factor interactions are aliased with each other. That means they're perfectly correlated with each other. We did taste testing for a response. The way we did the taste testings is small samples of all 16 blends were poured. And then we had a panel that tasted them in random order. And after every taste, you would write down your tasting notes. And then when we got to the end, you would independently rank the samples, with the best one being number 1, the second best one being number 2, all the way on down to the worst one being number 16. And we had a 5-person taste test panel. And by the way, you can probably see one of them was me, okay? And so when we got to the end, what we ended up doing was averaging the ranks. And over in that summary column, you'll see the average rank, and you'll also see the standard deviation of the ranks. This is a very good way to deal with subjective responses. I strongly recommend this forced ranking kind of idea. It really seems to work very well. It works generally much better than arbitrary scales. This is, like, oh, give it a rating from 1 to 10. Often you end up with your results being very clustered around a small range, and you don't get very much discrimination. This forces you to get discrimination. Okay, how did we analyze the data? Well, again, in course number 2, where we talk about fractional factorial designs and 2-level designs, we talk about calculating estimates of the factor effects and then plotting those effects on a normal probability scale. So the vertical axis here is normal probability, and the horizontal axis are the magnitudes of the effects. And on this plot, you typically will draw a straight line through the smaller effects that are near the middle of the plot. And then anything that falls off that line is probably important. And you can see that there are some pretty large, apparently large effects. G, for example, whole cluster, has a large positive effect. So increasing the amount of whole clusters does seem to have a positive effect on taste. D, the yeast type, has a large negative effect. So increasing or changing the yeast type from the low level to the high level actually had a detrimental effect. The main effect of F, barrel toast, appears to be important. More extensive toasting of the barrel didn't seem to help. And then there's an AD interaction that's significant. And you'll notice that I also included A in the model because the AD interaction is significant. And there's this principle we talk about called model hierarchy, where if you have an interaction term, you probably want to have both of the main effects. And we already had D, so I simply included A. Now, the problem is this is a resolution 4 design. And so that AD interaction is aliased or perfectly correlated with 3 other two-factor interactions. AD is clone of Pinot Noir and yeast, and I can believe that there could be an interaction there. Now, CF is barrel age and barrel toast, possibly. I mean, you might kind of believe that that could be important. BH, that's oak type and temperature. I'm not so sure about that being important. But EG, stems and whole clusters, is another, very plausible interaction. The point is you cannot distinguish between these interaction effects with the data that you have. Now, normally what we would do is we would run a follow-on experiment right away to try to de-alias those interaction effects. Well, you can't do that because we can't run but one experiment a year. And so this is one of the things that got me thinking over the years about better experimental strategy. Are there types of fractional factorial designs that we could use that don't have this complete correlation, perfect correlation, complete confounding of two-factor interactions? And it turns out there's a whole class of designs called non-regular designs that do have those properties. And here are some references to some of the work that I've done over the years on this. I've worked with a colleague of mine, Bradley Jones from JUMP, and we've done a lot of really kind of interesting work in this area. Here is an example of one of these designs. This is a 16-run, 6-factor non-regular design. We call this a non-regular design because, rather a no-confounding design, because there is no complete correlation between two-factor interactions. And here's one way to see that. This is a cell plot of the correlation coefficient between the model terms. And on the left is the regular 2 to the 6 minus 2, and the gray indicates correlations of 0, and the black is correlations of 1. And on the right are the correlations of the no-confounding 6-factor design. And you notice that there are some correlations between main effects and two-factor interactions, but the correlations are less than 1. And so that means that we could probably separate these two-factor interactions from each other if we had used one of these designs. So somehow I seem to have turned this off. Whoops. Okay. So you might ask the question, how did we do? Well, our first commercial release of wine was in 1990. And our 1990 Pinot Noir won a gold medal at the American Wine Competition. That's a huge national competition with several thousand wines. The 91 release got a silver medal. The 92 release won another gold medal. We were 6th best wine out of 2,000, best Oregon Pinot Noir. This winery has had solid growth over the years, produces now not only Pinot Noir, but other varieties. Wine Spectator loves it. The wines have done very well in international competitions. And here are just some of the ratings. And these are from the Wine Spectator, a very widely read publication. And you can see that these ratings are all in the 90 point and higher range. So the Wine Spectator loves the stuff. Just some pictures. There's the Chehalem tasting room in Oregon. There's one of our old labels on the right. And there's a couple of pictures of the bottles at the bottom, a couple of vineyard pictures, and in the picture in the center, that's Harry and I in the vineyard sampling one of our white wines, probably a Chardonnay, and he's trying to explain some of the finer points of viniculture to me, which probably, frankly, were lost on me. I enjoy the wine business. Harry sold Chehalem a few years ago and started a new venture called Ribbon Ridge. I'm not a partner in that, but I'm a member in his club. But I couldn't stay out of the wine business, and so now I'm involved in a new winery business in Southern California. There are 6 of us that are partners in something vineyard, or rather a winery called Belante Family Winery. We don't own vineyards. We buy fruit from Santa Barbara County. We make Rhone Reds, we make Viognier, we make Pinot Noir. We sell to a tasting room. The tasting room's in Mission Viejo. Here's the information. Here's how you find it if you wanted to visit. Okay, so that's the information that I wanted to share with you. But now I'm going to introduce Carly Metcalf to come in, and she is going to tell you about some follow-on work. Hello, Carly. Thank you for coming.
Oh, thank you, Dr. Montgomery.
She is finishing her dissertation here and is going to be graduating, and sadly she is leaving in August to go take a teaching position at RIT. So she's going to be a faculty member in the stats department, I believe. Is that right?
Correct.
Great. And her dissertation work is really interesting work because it's looking at these non-regular designs that I briefly mentioned and try to devise a really nice analysis method for these designs. Anytime you have a new design idea, you sort of need to propose an analysis technique to go with it. And this goes back to when central composite designs were introduced by George Box back in 1951. Well, how do you analyze a second order model? Well, there's this thing we call the canonical analysis, and that came out of that work. It made those designs useful. The same thing has been true in recent years with definitive screening designs. There's a very important type of modern design, not very useful unless you have a great analysis method for it. And you could say the same thing with computer experiments. You know, the space filling designs, useless unless you have something like a Kriging method to analyze the data. And so what Carly's been working on, and I'm going to ask her to tell you about, which is the subject for dissertation, is how do you go about analyzing these non-regular designs? How do you do that? What's the right way to do it? So you're up.
Okay.
You can have the pointer.
Thank you.
Great.
Thank you for that introduction, Dr. Montgomery.
Yeah, don't turn it off like I did.
There we go.
Okay.
Yeah,
right.
So like Dr. Montgomery mentioned, I'm going to talk about no confounding designs. So he did a pretty great job of kind of teeing me up here. You know, we talk about screening designs in this course and in the field of design of experiments. And as Dr. Montgomery showed with the wine example, they're really great when you have a lot of factors and you're trying to pare it down to find the vital few. And typically we like to think about them as first steps in sequential experimentation, and we like them to have a minimal number of runs because we don't want to waste our whole budget at the beginning of the experiment. You know, we probably intend to do some follow-up experimentation. And so fractional factorials, they're very popular screening designs. Here's a slightly different design than Dr. Montgomery mentioned. This is a 2 to the 6 minus 2, which is also resolution 4. And in this design, we have several two-factor interactions completely confounded with other two-factor interactions. So for instance, the AB two-factor interaction here is confounded with the EF two-factor interaction. But that was a regular design. Another type of design, screening design, two-level screening design, are non-regular design. So here's an example of a non-regular design, a Plackett-Berman design. And I think actually, Dr. Montgomery, you discussed these in the last Fireside chat.
Yeah, the Plackett-Berman designs are actually discussed in the course.
Yeah.
And there's a section on them in the textbook that even has an example of a Plackett-Berman design. And you know, for years, let me just jump in here for a minute, but for years, people were sometimes very reluctant to use these designs because of that partial correlation that you see between the two-factor interactions. And they said, well, how on earth am I ever going to untangle those? And they would end up doing things like using stepwise regression, which sometimes sort of seem to work, but not always. And so often you ended up in situations where you really had to do additional experimentation to try to untangle the interaction effects. But the thing that makes these non-regular designs so important is that there are lots of practical situations where you cannot do an immediate follow-on experiment, like our winemaking experiment. You know, the next time I'm going to get to run an experiment is a year later. And Carly has been working with me for the last couple of years on a DoD research project where we run into exactly the same sort of thing. You may be doing an operational test on, say, an aircraft system out at Edwards Air Force Base. And you may run one of these fractional factorial designs because you have lots of factors. And then you get to the end and you say, oh, golly, because of the confounding between these interactions, I don't know what's going on. I need to do another 8 runs. So you go to the people that run the test range and say, we need to come back for 2 more days to do 8 more sorties. And they just look at you and laugh and laugh and laugh. And they say, you know, the test range is booked for the next 8 months. You know, there's no way that you are going to fly your stupid airplane on our range until 8 months from now. So, you know, go home and, you know, put in a request. And so there you are, stuck, you know. And so, you know, she's done some absolutely fantastic research to help solve this problem. So I'll let you jump right back on it.
Sure. So I specifically was working with these no-confounding designs, which are non-regular. They're slightly different from the Plackett-Berman designs, but similar in that we have two levels, a high and a low, and we have this correlation amongst usually the main effects in the two-factor interactions and two-factor interactions and other two-factor interactions. So as I was thinking about, you know, maybe even comparing these designs a little bit or how to analyze them, I was particularly interested in this idea of estimation capacity. So for instance, with fractional factorial design, the example I showed previously, if I wanted to estimate a model that, let's say, or fit a model that says that had A, B, E, F, the AB interaction and the EF interaction, well, we can't fit that model. It's mathematically impossible because the AB interaction was completely correlated with the EF interaction. So I wanted to see, well, okay, how many models can we estimate? And so I looked at a couple of different designs. In fact, design 5 here is the fractional factorial, and design 13 and 18 are both no confounding designs. But we can see that the no confounding designs can definitely estimate more models. And I particularly like design 13. I think it's the best because of the estimation capacity here. And then there was a second piece I was also interested in when it came to kind of comparing these designs and also analyzing them. And that was this idea of model confounding. So, okay, great, I can estimate the model, I can fit that model, but is it differentiable from other models? So we'll go back to the fractional factorial example. If I fit a model that had the main effects A, B, E, F, and the two-factor interaction AB, and then I also fit a model that had A, B, E, F, and the two-factor interaction EF, those are going to look exactly the same. They're going to be identical. They'll give us the same Y hat. So we call this model confounding, where I can't differentiate between the two models. So that was kind of the second piece I was looking at was, okay, so how many models can I estimate? And then how many of them are unique, essentially? How many of them are not confounded with other models? And so using that, I kind of, as a starting point, I developed this model selection method called AIMS, Alias Informed Model Selection. And basically, we start with what we call a model space. And this model space is all of the estimal models that aren't confounded with any other models for a given design. So we figure out this space ahead of time before we even do any experimentation. And then we can go out and perform our experiment. And we have our data now. We have our response vector y. And with this and our model space, we can easily find the minimum mean square error model over this space. So which model out of the whole model space gives us the best mean squared error. And then we can also find a minimum AICC model, the corrected IK information criteria. These are just two metrics we can use to kind of assess model fit. And then when I'm looking at these two models and looking at the alias structure of the design, we can add these like rules, I call them decision rules, where based on the alias structure of the design, we kind of pick a better choice between these two. So for example, here's design 13, my favorite no confounding design for 6 factors. If you wanted to create this design, you could start with a 2 to the 4 factorial and generate the E column using the 4 factor interaction, and then the F factor using that formula there. And so we can easily generate this. We see that we have correlation between the 2 factor interactions and the main effects. So we can use this design to come up with our model space. Here's the model space for design 13. It's ended up being a total of 1,238 models. That's how many models we could fully estimate and that weren't confounded with any other models. So pretty good. And it turns out that it was all we could fit any model with up to 1 2-factor interaction, and we could fit any model with up to 4 factors, even all 4 main effect 6 2-factor interaction models. So quite a few in our model space. And then to develop these rules, I look at the alias structure. So this is the alias structure for design 13. We can see all the different relationships here. And I created a series of rules, but for example, one of them had to do with the AB interaction. So from this, we can see that both DF, the DF 2-factor interaction, and the EF 2-factor interaction are correlated with the main effect C. And they're also both correlated with the main effect AB. So I created this rule where if the minimum mean squared error model in my analysis came up and it had the main effect A, the main effect C, and either the DF interaction or the EF interaction, I thought, hey, those are all really closely related to the AB interaction. We could be masking that effect with these in the model. And typically we see that the minimum mean square error model will have more terms than the minimum AICC model. So if I see all those effects in the minimum mean squared error model, I go and I check the minimum AICC model. And if that does have AB, I swap and I say, hey, all right, the selected method or the selected model is going to be the min AICC model. So that's just an example of one of the rules, but I created several that had to do with this kind of alias structure and what I thought could be happening for with respect to them being kind of confused for each other, or a pattern where maybe several effects were getting selected over a true effect. I have a quick example here. This is a model I kind of made up, but it has a main effect A, B, C in a 2-factor interaction. And I use this model to generate random data from it. So I generated data from this model using a standard random normal error term. And then I tried to use my method to see how well it could identify these effects. And one way I tried was stepwise regression, which Dr. Montgomery mentioned earlier. This is kind of a typical go-to way to analyze designs like this. And it selects the main effects A, C, E, F, the 2-factor interaction AC, and the 2-factor interaction EF. So not quite what we started with. We should have had the main effect B in there, and we should have had the AB interaction. And we have a couple of type 1 errors too, right? A couple of things that we said were active that weren't originally active. But now if we check out the AIMS solution, the Alias Informed Model Selection, if I use my design space, those 1,238 models, I can find the minimum mean squared error model. And it turned out that that was A, C, E, F, and 4 two-factor interactions. And then I could also find the minimum AICC model, which was A, B, C, and AB. And since the minimum mean squared error model had the main effect A, C, and the two-factor interaction EF, that triggered one of my rules. So I'm going to check out the min AICC model. It does have AB, so we're going to swap it. We're going to say rule two is used, and we'll select a min AICC model. So that's how kind of AIMS works. And then I did a really large scale kind of simulation. I looked at lots and lots and lots of different models, and I compared the AIMS method versus stepwise regression and 2 other model selection techniques called the lasso and the Danzig selector. And the AIMS solution did really well overall. So I looked at the proportion of models, or the percentage of models where the model selection method found at least all of the correct terms. And AIMS did that in 98.4% of the models. So it does pretty well, especially compared to some of the other model selection strategies. So that's what I've been working on, and I'm trying to kind of think about ways to expand this to other designs and how we can think about this general method in non-regular designs and other places with more factors.
Yeah, this is really very important work, because these no confounding designs have great potential to reduce the amount of experimentation that people have to do. And ideally, you would have a routine in a package like JUMP that lets you select one of these designs, and then it would have an analysis method coupled with it that would give you a likelihood of getting good results. And JUMP already does that for definitive screening designs. And so they could certainly, we could certainly do that here. And she's been a little modest about this, because she's already handled the 7 and 8 factor case. So that takes care of the non-regular designs that are really equivalent to the regular resolution 4 designs. And so there are these non-regular designs that go in some different directions. Some of them have more than 16 runs. Some of them have 16 runs, but more factors.
Sure. So
there's lots of possibilities here. And so, we're just sort of, I think, just lifting the rock a little bit and seeing what's underneath it, on these designs. So now we're going to get around to some questions, and feel free to jump in and answer some of these questions with me if you would want to. Here are some that we've already got. Can you share some demonstrations on Design Expert and Minitab software on performing various designs? Well, we didn't really do that in the course, because we felt like it might be a little bit too much to push a lot of different software demos out on you. But both of these are very good packages, and they do a very good job. Almost anything you can do in JUMP, you can do with Design Expert, you can do with Minitab. JUMP has a few features, a few more features that these packages don't, but they're all very, very good. And both of these organizations, both StatEase, that makes Design Expert, and Minitab, they have places on their websites where they have demos. And there used to be something called Meet Minitab. Is it still around? Do you know?
I'm not sure.
Yeah, there used to be something called Meet Minitab, and it was a really good way to get an exposure to what these packages do. Okay, the second question is, how can response surface plots simulate actual environmental conditions? Well, what you're getting from a response surface plot is essentially an average response over the conditions that you have chosen to experiment with. If some of the variables that you've experimented with are environmental factors, then the variability from that will be reflected in confidence intervals around either the line, if you're doing something like a prediction profiler, or around the contour plot. So I think that's one way that those that kind of variability can be accounted for. And then I really like this last question: why are these kinds of studies becoming obsolete nowadays? Specifically with regard to why are coding and simulation getting more priority? Well, it's because the people that are doing the coding and simulation are not well trained in using experimental design. So once you've got a simulation model, what are you going to do with it, right? Are you just going to sit there and play with it? Well, why don't you run a design experiment on your computer simulation, okay? If it's a stochastic simulation, everything we've talked about in this course works. I did this for years, and it works great. If it's a deterministic computer model, something like a finite element model or a computational fluid dynamics model, there are classes of experimental designs called space filling designs that we use for those, and they're mentioned in the course, and there's material on that in the textbook at chapter 11. So part of the problem is the guys doing the coding and simulation haven't learned anything about experimental design, and that's a gap in their education that needs to get fixed. These techniques are perfectly applicable to these kinds of problems, and they'll make your life a lot easier and a lot simpler. Okay, so get with the program, guys. Wake up. How important is understanding experimental design for a data scientist? Really critical, because a lot of data scientists view that their job is to go out to the web and gather in large amounts of data and just analyze that data somehow and try to learn what's important. Well, it's very difficult to learn cause and effect from looking at that kind of data. I regard a lot of what data science people do under the term of data mining as what I call hypothesis generation. You're figuring out which hypotheses that you need to test. Now you go out and you run a design experiment to verify that, in fact, or to try to see whether what you think you've learned from this big data mining exercise is actually worthwhile. Some people do something called A/B testing. These are web-based experiments, by the way, run in marketing organizations all the time. By the way, I've got a couple of guests lined up to come in that are going to talk to you about A/B testing. So we're going to talk about that. That's coming up in another Fireside chat. These two guys are both former PhD students of mine, and this is what they do for a living. They do this kind of stuff. So we're going to get to hear from them about this. But experimental design is a really critical, important topic for people that do any kind of work with data, because so much of what we do is dealing with, well, what I think of as historical data. And you can learn a lot from looking at historical data, but you can also be seriously confused. Let me give you an example, okay? Let me give you an example of this, okay? Years ago, when I was a faculty member at Georgia Tech, a colleague of mine was doing some consulting work for a company up in North Georgia that made carpet. Actually, they made a resin product that was used for the backing for indoor-outdoor carpeting. And he said, these guys having some problems with this stuff. Would you come up and talk to them? So sure I did. And it turns out that they were having some problems with the chemical properties of this material. And it looked to me like they needed to run some experiments to figure out what the important factors were. So we set up actually originally a fractional factorial design, and we wanted to run this thing. And then one of the engineers said, well, you know, we really need to talk to the boss before we do this. Okay, so we go talk to the guy in the head shed, okay, and we explain what's going on, and his eyes are glazing over, and he says, so you're just going to run this experiment to produce data, right? And in my, basically naive way, I said, well, yeah, that's what we're going to do. And he says, well, you realize that we've got data on every batch of this stuff that we have made since Moses came off the mountain with the formula. Okay, so Go analyze that. So sure enough, you know, they had data on all of this stuff for years because they'd been making it for years. So I hauled this data back to Atlanta. I bought myself some time on the Georgia Tech computer and I started analyzing it. And after a week or so, I thought I knew some stuff. And so I went up to see these guys again and I said, okay, here's what I think is important. This looks like it might be important. This looks like it might be important. By the way, this variable over here, this temperature variable, I don't think that's important at all. And I noticed the engineers are starting to snicker a little bit. You know, and when the engineers are laughing at you, you know you got a problem, right? And one of them said, well, that can't be right because we know that variable is so important. That's why we control it so closely in the process. They had a PID controller on this thing. It never changed. By the way, if you want to find out what happens when you change a factor, what have you got to do? You got to change the factor, right? Yeah. And in so much of this data that we go out and mine from various sources, the important stuff doesn't change. Or if it changes, as it gets bigger, another variable gets smaller. And the cross correlation between the two may cancel the effects out. There's, you know, you just have to be very skeptical of anything that you learn from these kind of exercises because there's so much other stuff going on that it's hard to figure out what's going on. Okay, I am trying to design a leaching experiment based on a lit review. There are 4 main factors influence it. The main factor already known. Should I carry out a pre-screening or go straight on to using RSM? Do the screening. Do the screening. Another great war story, okay? This was told to me by one of my former PhD students, okay, who was trained in metallurgical engineering, okay? And she was working for a company where they had a heat treating process. And they were having trouble with the straightness of the shafts that were coming out of this heat treatment. And these shafts were used in like auxiliary power units for aircraft. So they got to be really straight. So she said, we decided to run an experiment on heat treating to see if we could figure out what might be going on because everything was straight going into heat treat and then it comes out of heat treat, not straight. So they're getting ready to do this and this experiment is going to be time consuming and it's going to tie up some production equipment. And one of the big bosses, once again, said, don't do this. Don't put that variable. We already know that that variable is at the right level. Yeah. We've already optimized it. Mm-hmm. Well, Diane was pretty smart and she refused to knuckle under. So she put that variable in the experiment anyway. And it turns out that that was a very important variable and it had not been optimized. It was in fact at about the worst level you could possibly choose for that variable if you wanted the shafts to be straight. So be leery about what you learn from the literature or what the folklore is. Put in all the factors that you think might be important, run the screening experiment and see what happens. What about choosing the levels for an experiment? Well, I think that this is where you need to talk to the operating personnel. Operating personnel often know a lot about this. I always tell people that you know, the engineers know a lot, the operators know a lot, and very often those two sets of knowledge don't perfectly overlap. There's things that they know that you don't, and there's things that you know that they don't. And this is a place where you need to definitely talk to people that have some operational skills. If I understood Dr. Bingham's explanation well, blocks allow us to absorb some uncontrolled variables and uncertainties. What if instead of, so you have more than one? So basically you should be able to determine from the analysis what the size of the block effect is on each response, because you'll do a separate analysis on response 1, a separate analysis on response 2, separate analysis on response 3, and so on and so forth. And you can look at the size of the block effect
Mhm.
for each of those individual responses. Does that make sense to you?
Yeah, yeah.
Okay, I think that makes sense. Okay. Technologies like data science, big data, will kill DOE. No, large amounts of data simply make it easy to get the wrong answer to a higher level of precision. Designed experiments are the only way that you will ever discover cause and effect, okay? And if what you need to understand is cause and effect, these are the ways to do it. The major challenges are education. A lot of the people that are into this data science, big data, artificial intelligence, whatever, they know no statistics. They have never taken a course in experimental design. They're computer science people. Nothing wrong with a computer science person, but they need a broader education. As soon as you understand the power of designed experiments, you see immediately the potential advantage. Coupling designed experiments with data mining is a way to really make things happen. All data mining, artificial intelligence, big data, all that's going to do is generate hypotheses. Those hypotheses need to be tested. And the way you do it is with designed experiments. Okay? It's the only way to learn cause and effect. Sorry, I wish there was a simple answer that said it was going away. Okay, I'm doing a plant tissue culture experiment with many factors. And my response is either callousing, which is observed or not. Okay, should we consider all the test tubes around 30 replications? I think what you probably need to use is the percent of that 30. Mm-hmm. Does that make sense to you?
Yeah, yeah.
And then the analysis would be some sort of logistic regression model fit to the data. And software packages can do that. The logistic regression model basically you can use it in conjunction with a designed experiment. So that's how I think I would do it. If callousing could occur at various degrees, then maybe you could use a forced ranking type system, like we used in the wine experiment. Look at the data or look at the tubes and say, well, this one has more callousing than this one, and so you can rank order them.
Yeah, that's a great idea.
So you might be able to do that. I sort of like rank ordering as a way to do things. It works really, really well. But if it's strictly 0-1, so it's percentage of callousing across the 30 tubes, you're going to have to fit a logistic regression model to the data. Does that make sense to you?
Yeah, yeah.
Yeah, and you did you do any examples of logistic regression model fitting in the jump tutorials?
I'm not sure.
I don't think you did. But there is an example of this in the textbook.
Yeah, right.
Yeah, if you look in the textbook, there is an example of at least one experiment where the response variable is a proportion.
Yeah.
And I believe it's a jump example. Yeah. And I'm sure you could also go to the jump website and find an example.
Jump help is really helpful.
Yeah, Minitab can do this too.
Mm-hmm.
Okay, that seems to be it. I have one more question I want to address. And this is a question from last time, okay, that maybe I didn't give the best answer to, that I'd like to revisit, okay? And this question was, the people that are running this experiment don't do it the way I planned. They change the run order and they do all kinds of things. And how do I stop that? Well, they're doing that because they knew some things about how difficult it was to run the experiment that you didn't know when you planned it. And I mean, in many cases.
Sure.
And I think one of the ways to deal with that is to get them involved in planning the experiment. I always kid my students. I have some what I call Montgomery's theorems of running experiments that I talk about. And theorem number one, Montgomery's theorem number one is, if you want it run right, do it yourself. Now, we all know that that's not possible, right?
Not always.
When, Carly used to work at Corning. She was a statistician and research engineer at Corning. I bet you designed a lot of experiments that you couldn't run yourself.
Correct.
Yeah. So the corollary to Montgomery's theorem is, if you can't run it yourself, be there and watch what they're doing.
Yeah.
Okay. Ask questions, you know. And an even better corollary is get the people who are going to run it involved in designing it.
Mm-hmm.
Because if there is a variable that's really going to cause a problem, they'll tell you about it. Yeah. And then you can come up with some sort of workaround, such as a split plot design. Sure. So you know, getting a lot of different people involved at the early stages of design is really important. Engineers, operators, your QA people, even people that deal with customers. Yeah. And I suspect in some of the stuff that you did at Corning, it was in response to customer issues. Yeah. So what about using, this is another question that just popped in, what about using a Plackett-Berman design for the plant tissue experiment? Could it bring us info about which factors have more activity? Is it correct? Well, certainly you could use it. I would wonder about how many variables you have. If you don't have a rather large number of variables, I would be inclined to use a regular design, although, you know, when you get in the range of 8 to 10 factors, you know, you start thinking about Plackett-Berman designs because they can save you a lot of runs. But as of the moment, your only analysis method for dealing with that are things like stepwise regression. Yeah. And doing stepwise regression with binary response data is a little tricky. Yeah. So you might, it's hard to answer this, because I don't know much about the number of factors and, you know, how many levels and things like that. But I'm a big fan of non-regular designs, and there are many places where they make a lot of sense. Mm-hmm. Where individual runs are very expensive, or where there's a fairly, you know, moderate to large number of factors, and follow-up experiments are difficult, tricky, maybe impossible. Yeah, maybe impossible. I know with the DoD people that we've talked to over the last few years, this is one of the big problems that they constantly face, is they have a lot of factors, and doing follow-on experiments is often just not easily doable. Mm-hmm. And so I think some of the work that she's been doing is going to be very useful for our DoD folks. Okay, that's the end of it, I think. We're done. Oh, Megan has given me the high sign that maybe we're not done. Megan feeds the questions to us. Oh, she's got another one, it looks like. Oh. We're close. It's coming, I can tell. Oh, this is so hard. How can we change companies' culture in order to get a sponsor to some project. You know, you would hope that in this day and time, this isn't as much of a problem as it used to be. But it was something that I always dealt with when I did consulting work for companies for many years. And it was usually trying to find a way to work from the ground up. You know, finding some group of people inside the company that they had some influence that you could talk to and work with and get them to help you grease the skids, so to speak. This isn't nearly as much of a problem as it used to be in most companies because of Deming and the work he did and Six Sigma. Six Sigma has changed a lot of people's opinion about things like this. Plus, I think in many cases you can find examples. You can find articles. You can find video presentations showing the power of these ideas. And if you get people to pay attention to that, you have a chance, don't you think?
Yeah.
Did you ever have to fight with this at Corning? Was this much of an issue?
No, thankfully we had a lot of leadership that believed in this methodology, and we didn't have to convince too many people. But it is important to have a champion, a sponsor.
It sure is. It sure is, because it does require some resources to do this. Sometimes it requires some training. You may have to go out and acquire some software. So yeah, it's important to have people in leadership that understand the importance. Good question. All right, I think we're done for today. And yeah, Megan's given me the high sign. We're done for today. And we will be back for another fireside chat in about 3 weeks, I think. I think the next one is the 29th. August 29th. August 19th. It's good because I know the school starts the next day, whenever it is, and I always showed up a week late for class. So, okay. Thank you. Hope you enjoyed today's presentation.